Hi everyone. Today I'm talking to John Martins about a particular quantum computer architecture that he built in the past. This architecture is superconducting, and what's particular about it is that the qubits involved are adjustable in terms of their frequency, which allows you to have resonance, let's say, between multiple of the qubits at the same time. I'm going to let John introduce the investigations that have been made in the paper, and I hope you enjoy what he has to say. John, thanks for taking the time to join today.
Yeah, thank you. I'm glad to be here.
I'm sharing the paper now that we'll be discussing on the screen. It's called Computing Prime Factors with a Josephson Phase Qubit Quantum Processor. I think for us to get started with this paper, maybe if you would mind describing what a Josephson Phase Qubit Quantum Processor is.
Okay, well, there's a variety of physical qubits that people are making around the world to make a quantum computer. And this is using superconducting devices, and where you're basically building a quantum state using electrical variables, let's say the current and voltage in electrical circuits. And Josephson qubits work because they're superconducting, so they have very low amounts of dissipation. And by combining a Josephson junction and the capacitor, the Josephson junction looks like a nonlinear inductor. You have a capacitor. This looks like an inductor capacitor, nonlinear inductor capacitor resonator. And following the laws of quantum mechanics, you're going to have states, quantum states in there. And you basically use the two lowest states of that system, the ground state and the first excited state, to act as the qubit. And then you use kind of the nonlinearity of the Josephson junction, so that if you make a transition from the 0 to 1 state, the 1 state to the 2 state transition is a different frequency unless you don't see that transition. And then the nice thing about the Josephson devices is you microfabricate them in a clean room, so that you can make a device. You can have a lot of flexibility in how you make the devices. There's a lot of different qubit types. And then once you make, one or two, and you know the physics behind that, you could use the scalability of microfabrication to print more and more of these devices and scale up your quantum. Now, what's kind of unusual about this is that people are used to the concept that quantum mechanics is the law of nature for microscopic entities, atoms, very, very small entities. But in fact, this is quantum mechanics that's shown in a macroscopic device. It's big enough that, with good eyesight, you can see the device. It's not small. So quantum mechanics is not that physics is small. It's just some basic physics that if you're in the right conditions, you can see. And in fact, it's kind of unusual with this system in that you're seeing quantum mechanical behavior when you have a system consisting of, billions, trillions and trillions of electrons in a metal. So it's the quantum mechanics of a macroscopic object, in this case, an electrical circuit. And that actually hadn't been understood and demonstrated prior to the 1980s for my thesis project at UC Berkeley, where we did that. And in the end, there's been a lot of different experiments building now macroscopic quantum objects, and it just expands the amount of systems where you could understand quantum mechanics and use it. But more importantly, because it's big and macroscopic, it's a little bit easier to bring your control signals in and control it, and then to build up a quantum computer. And I think that's one of the big reasons why superconducting qubits has done so well, especially in the last 10 years since this article. Because once you understand how to get into the conditions and make it right, because it's macroscopic. So it's a little bit easier to build up and scale up to make a complex system.
I think at the time of publication, the architecture that you're proposing, and we'll also have a look at that in a second, was the first one to be implemented, or at least with Shor's algorithm, from a solid state quantum bit system. Could you maybe compare the architecture, like inside the scope of superconducting quantum devices now, to the other architectures that are out there, and why this one is sort of special, or what sparked the interest for that investigation?
What's interesting is, this particular architecture that we used here was fine for this experiment, but the architecture actually developed and changed over time to do it in a different way. So I'm going to let you zoom that in. I mean, it's a common architecture, where you have this qubit, it's coupled to a resonator, and then coupled to other resonators. And this was the architecture we had developed at the time and was able to do this kind of experiment. But it turned out that subsequent to this, we kind of changed the qubits and changed the architecture. And, we moved on to something else. But the thing about this architecture is it contains all the common elements that you need. You have qubits, you have resonators, there's a bus where the qubits talk to. In this particular case, we had a qubit where you could change the frequency. And that was one of the essential ideas that we brought forward. As we did this. So this was kind of the culmination in terms of that of a particular architecture. It was in 2009, and soon after that we changed a little bit. But the basic components there are the same and basic operating principles. And I would say the biggest thing that we did here was we made a qubit where the frequency, the difference in frequency between the 0 and 1 state, that could be tuned up and down. So if you have a resonance and you have a tunable qubit, you can bring it off resonance where basically they aren't talking to each other, and then bring it on resonance where the two systems are talking to each other, and then the states can couple back and forth. And that was the essential idea brought forth in this experiment and others that we took forward. And the interesting thing is, at the time, people didn't think this made much sense at all. This was considered something you always wanted to keep the qubit frequency constant and then do a lot more complicated things to get it to work. And looking back, I almost lost my funding because this was considered so crazy of an idea. People didn't think it would work for good reasons, okay? And then, we were just doing something different. In the end, what I wanted to do was maximize the amount of controllability so we could turn on and off these interactions quickly. And then we'd lose some coherence or things would be a little bit harder, but I decided that, that would work out okay in terms of the whole system engineering. And that idea turned out to be pretty good because we were able to build these transmon kind of qubits and then eventually do the quantum supremacy experiment at Google. And it was published in 2019.
Can we dive a little bit deeper into the tunability of these qubits? So we have an architecture here, and maybe we can actually leverage that to talk about it, but how, in principle, do you construct a qubit that you can tune? What is the parameter of this system that you change in order to change the frequency of the qubit?
What you do here, so what happens is when you have a Josephson junction, it has a nonlinear inductance. And as you put the current through the Josephson junction that's closer and closer to what's called the critical current, then it changes the inductance and makes the inductance bigger. Okay? So if you're at like low current, it's one inductance, and a higher frequency, you put more DC current through the device, it has bigger frequency, bigger inductance, and the frequency goes down. And you excuse me, you have to go into the physics of how the Josephson junction works. But these are very simple equations that describe that. So what you do, you see in this diagram here, where you see Q4. There's a loop of the X at Q, where the Q4, that's the Josephson junction, and then there's inductor to the right. And what you do is you put current into the little drive line to the right there, on the lower end, right? And then that puts magnetic flux, which drives current around that loop, and then as that current goes through the junction, that increases the inductance and the frequency goes down. So that's the basic physics, and it's very fundamental to how the Josephson junction works. It's just essentially a nonlinear inductor. And this is really the amazing thing about nature. The fact that you can make this strong nonlinear inductance out of a superconductor, which basically operates perfectly. There's no loss mechanism to it that we know of. It's a very simple relationship. And, if nature hasn't given us this very beautiful relationship, we wouldn't be talking today because this wouldn't be possible. But somehow makes this element to be extremely pure, free of defects, even free of macroscopic defects, it turns out, don't matter for it. And because of that basic fact, we can build these whole host of devices to make it work this way.
Mm-hmm. Yeah, it's really quite cool. I think one thing that's interesting here is the bus, I think, in the middle. So I think that's represented here, and then also in the actual architecture with with the B here in the middle. Can you describe what the relationship is with this thing, with the bus, to the qubits? What is the reason for having that in the architecture?
Again, this particular architecture we moved away from, but it is an important element. A lot of other people continue to use this. But basically, this bus is just a standing wave in its coplanar resonator, and this standing wave is just like if you hear, you just have like an organ where you have pipes of a certain length that emit a certain frequency, and as you go to a shorter length of a pipe organ, it's going to go a higher frequency. So it's the same physics, it's just a standing wave. And that's a resonator, and the qubits are a resonator too. Okay, so they're both building this electromagnetic resonance. Okay, mm-hmm. And the difference is in B, the physical resonator, that's a linear resonator. So that means that if you drive it harder and harder and you have a higher amplitude signal, the frequency of the oscillation is the same. Whereas in the qubits, what happens is when you drive it with more and more amplitude, then the frequency goes down. Okay, and that's called a nonlinear resonator. And you need that to make a qubit in order for the 0 to 1 state to be a different frequency between the qubit 1 state and the 2 state. That way you stay in the 0 to 1 state. Mm-hmm. Now, even though it's the linear resonator is you can't make a qubit operations there. You can use it to store information and to transmit information from, say, Q4 to Q2. So you have information from Q4, you send it to the bus B, and then you by putting it in resonance. And then you put information in, you bring it out of resonance, and then in Q2, you then bring that into resonance and swap the information again. So it's possible to connect Q2 to Q4 indirectly through the resonator. And other people in the field have used this basic idea and been able to make quantum gates and really develop this idea very, very extensively. I would say our approach after this paper was actually to get rid of the bus and have them interact directly for other reasons. So, yeah. This
Could we
was
maybe get into that a little bit as well?
experiment.
Like how, sorry?
Go ahead.
Could we maybe go into that a little bit as well? How they interact nowadays? Let's say, like, what changes you made in architecture from using this bus. So I get what you're saying. You can use the bus to put the qubits into resonance. And the reason why I'm sharing this part of the picture now as well is this is a frequency diagram essentially for the different qubits. So as you move them down in this figure, you would end up in resonance with the bus. And then if you take two of them, you can transfer the information. That's clear.
Yeah,
I suppose there's a reason why.
What happened is we really pushed this idea and was working on it where you change the qubit frequency so that you could turn on an interaction by having two frequencies be the same and then turn it off by moving it away. And I would say other people were doing other things and looking at different kind of gates, and we did this, direct frequency change, and that's really the basis of this paper and what we did for the next 10 years. Okay, so how does this work? Well, it's basically a resonance phenomena. This is well known in classical physics. You have two children on a swing, and they're coupled together, by holding hands or something. And if you have one person started swinging on one side, then eventually the other side will start swinging, and then the oscillations go back and forth from this one to this one, and then back and forth again. And there's a quantum version of this that does exactly the same thing. Where you have, coupled oscillators. But for the coupling to work, they have to be at the same frequency. If they're at different frequencies, then, it still drives the other one, but because it's at different frequencies, it's extremely ineffective and nothing basically happens. So, and this is like, tuning your radio. Of course, you don't manually tune it anymore, but you basically tune your receiver to a transmission station, and when it's tuned right, you pick up the signal, and when it's tuned off frequency, you don't see it. It's a very basic principle, and that's the principle here. And this diagram really illustrates that. That was kind of the view in our mind. We kind of have beads on a string, and you can turn it off, and then you can turn it on by putting them on resonance. So you have qubits where you can move up and down and turn them on and off resonance, and you also have the bus where you can do the same thing. And in this particular case, we were going from the qubit to a bus and then to another qubit. But later on, we just did qubit coupling. That turned out to work really well.
How do you make the qubits interact directly? Like, I'm assuming it's easier to have this interplay with the bus in between. I would naively think about that as some form of anchor point where you can get that into resonance and there would be sort of a strong source that you could then transmit the information to the other qubit. What kind of architectures came subsequent to this paper that allowed you to interact with the qubits directly?
So what we did is here we had capacitance from the qubit to the resonator. That's the black capacitor signal, which you see there. And if you scroll down scroll down a little bit more so you can see the picture of the device. No, up. Excuse me, up. You can't really see the capacitor structures, but you can kind of see that. There are little capacitors between the qubit and the bus, and basically all you do is you bring the two wires together, And then, that kind of it's not, near overlap is where you get the capacitance. And all you had to do in this case is, instead of going from a capacitor to the bus, from the qubit to the bus, you just do qubit to qubit. And in that case, you can have direct qubit coupling. And that's the nice thing. You're building an electrical circuit, so you have lots of flexibility in how you want to architect the devices. So if you can go to a resonator, you can build a capacitor between qubits. That's very easy.
Okay. One other question I would have on the architecture here relates to these memories here. So the memory resonators, I think they're called. You have 4 of them. Would you mind describing what the role of those are in the wider architecture?
Well, like I say, we were just playing around with different ideas of architecture. In this particular case, you have a memory of the qubit, and you could bring the qubit. Of course, the memory resonances are different than the bus resonances. So you can bring the qubit, so the bus might be here and the memory is down here. So you can bring the qubit down to the memory resonance and then swap a state in. And then sometime later, bring it on resonance and swap it out. So it was idea for an architecture, and we were just exploring how all that worked. The bus was to couple the qubits together, and the memories were to store the qubit states. And then, and this was fine for this experiment to show how it worked. What happened is when you have to swap the states and do all this, it takes longer to make your gates, and then you introduce possible errors. And what we decided afterwards is to eliminate kind of all that overhead and then just directly couple the qubits together. And, so we kind of went, this was a nice thing at the time, and there were some experiments we could do at the time, but we moved away from that, afterwards. But it was very good to demonstrate that we could turn on and off the interactions in a clear way.
If we talk about memories for another second and talk about it from a more general point of view, this is one instantiation of how you could introduce a memory into a quantum architecture like this. If we're talking generally about how you maintain the information throughout the computation and potentially afterwards, if you also need to maintain it for some amount of time for the readout, let's say, how do you do that now? If this is not the, let's say, strategic architecture for these kinds of systems when it comes to the memory component, what do you do now to preserve the memory?
Yeah, this is a really good question. Actually, it's a very subtle question. In classical computers, you always have the concept of memory and computation. And, it was natural to try to introduce that here. What we found by doing this experiment and thinking about it is the concept of memory at this low level isn't really that helpful. The people have done a lot of experiments on memory and shown various things, but it's not that helpful. And the reason is you have to transfer the information into the memory and then transfer it out. And even though the memory might be much better than your qubit, you lose fidelity during your transfer time. And that's, you don't kind of get a net gain to it. And also kind of at the low level, you want to have your memory into the qubits. It's just like in a CPU, you use regular registers, which are just, logic gates when you're doing the low level computation. So since we're kind of doing the basic computation, and since you tend to lose coherence when you swap in and out of memory, it's not such an ideal generic concept that people tend to think. And one of the reasons we understood the concept of memory was around this time we started working on error correction codes and the surface code, and we really started to understand how error correction worked. And what we decided is to make error correction work, you just have to have a lot of good qubits, and that memory wouldn't help you much. Okay, and so then we just said, well, let's just focus on making good qubits, making good gates with qubits, and that we kind of redirected our focus in that way.
Okay, so would it be fair to say that in the kind of implementations that you're building now, you normally exclude this kind of component altogether, and the only memory, so to speak, that you would use is the one inherent to the qubit as you do the computation?
Yeah, okay. and although to me that's the right way to proceed at this time. Obviously, if you could, and other people are working on it. Obviously, if you could make a good element, that would be nice. But it's actually much harder to make that memory element, because it's not just that the memory has to be good, but you have to connect the memory to your qubit. And that transfer process tends to make your memory not effective. Okay, when you go through how the math of all it works. Now, maybe someday someone will invent that, and that's really nice. But when we went through, how you practically used it, it was not as good of an idea as we thought at the time.
Okay. If we look at the architecture, one more question I had is what these things are on the sides. If we look at the diagram down here, I don't see a direct equivalent or a direct correspondence, let's say, to whatever these things are on the sides here.
Sure. Those are the contact pads. So the wires that go off the chip have to be connected to something. So if you look, let's say where your arrow is right now, there's a piece of copper, okay? And that copper is on top of a very thin sliver of a printed circuit board. And that's where the signals come in. And if you see just up and to the left of that, you see some wire bonds going from the copper down to the chip. So, that's where my cursor is. Okay, your cursor. Sorry. Can you move your cursor just a little bit to the right and up?
You mean here?
Yeah, right there. That's the copper circuit board that's coming in, and then from that you see the wire bonds to go into those pads. So those are just pads that you connect the wire bonds to go to the external chip. And obviously those pads are enormous. They take up a lot of area of the chip. We made them smaller in more advanced devices. We also made this copper fingers a little bit better and figured out how to do that a little bit better. But yeah, you have to connect the chip to outside control circuits, and that's how we did it.
Is that still one of the key problems with scaling up these kinds of architectures in general? I'm thinking now about superconducting ones.
Yes. So this is an early version of what we did that worked well. In fact, when I was at Google and we were working on the quantum supremacy chip with 100 and something contact pads, I was involved in the mount. I designed the mount. I designed the way the circuit board worked and all the little things. That's actually a tricky design problem because you want to make it small, but there's some other constraints to it. So we improved a lot of that over the years. This was a very early design to figure out how to make the devices properly.
And in the large scale devices, so talking about the ones that Google built, for example, when you have a massive amount of connectors going into the chip, is the interference between those wires leading into the chip one of the bigger problems? Or when it comes to these kinds of
you have to worry about crosstalk. It's called crosstalk, and that's a big part of the design and understanding it. The basic idea though is the smaller you make everything, the more ideal it is to a perfect transmission line, and you get less crosstalk. But of course, you can't make it small, and if you have a lot of wires, they're going to be close together. So this is something we worked on. Now, just to give you an example, in these things we put pulses into the system to control it. And when people started this, other groups were putting pulses in, and you were having crosstalk of about 30 or 50%. Okay? And then if we saw that and we improved the way that you do the chip, and we got it down to 1% crosstalk. And at 1%, you can put compensating pulse. So if you have crosstalk from one line to this line, what you do is when you put a line in here, we put a compensation negative pulse on the nearby line to get rid of it. So you can calibrate that out. But that was 1%, and then we started working a little bit harder, and it was 0.1%. And then finally, by the time we got to the quantum supremacy chip in 2019, it was down at 10 to the minus 4, almost 10 to the minus 5, okay? So, this is things you can engineer over time. You have to understand what's going on, understand the principles, but yeah. And, again, that's one of the things you just have to learn over time how to do it. It's a little bit tricky.
Mm-hmm. Okay. Before moving on, the last question I would have on sort of scaling up the architecture is, what, besides the crosstalk that we have in the wires, are the main limiting factors when it comes to scaling up the leading architectures, let's say, of superconducting quantum computers? Not necessarily this one, because I take that it's an early version, but...
what happens is, I'm gonna answer it at a very high level. The real issue here is to do systems engineering. And system engineering is not fixing one thing. It's that you have 10 or 20 things you're worried about and making all of them work well at the same time. I mean, I just talked about crosstalk. That's that's probably number 20 on my list, but you have to solve that, okay? So there's many, many things you have to solve to get it to work right. Now, when people talk about qubits in the press, they always talk about how many qubits you have, okay? Right. And obviously you have to have a lot of number and you have to be able to control them. Yeah, okay. But in my view, and that's something that's worth talking about, but in my view, much more fundamental is controlling the qubits without error. So you do some control signal and you'll know exactly what that qubit did, okay? And what happens is there can be intrinsic mechanisms where you lose the quantum information. There can be a calibration error where you thought you did something, but it did something slightly different. It could be crosstalk where you control one qubit and another qubit interacts a little bit in a way you weren't expecting. So you have to budget all of that. And I'm going to say what's nice is there's a variety of qubit systems where you can do qubit operations at the error rate of, let's say a few percent, 1%, a few percent. And you can do a lot of interesting physics of that. But if you really want to start doing something useful and do error correction, do all these things, you have to bring those errors down to a part in 1,000, 0.1% or maybe even lower. And that turns out to be really hard to do. So, you have to solve many problems, many system problems. But I'm going to say the qubit errors are the number one thing in my mind. And when I give talks about quantum computing and talk about what the future is, I always emphasize that because it's hard and people tend not to want to talk about it because it talks about the faults of your system, the things that aren't going so well. Everyone wants to be optimistic. I get it. But you really have to fix this, okay, in all qubits. And the nice thing in superconducting qubits, people have been slowly making it better. There are some nice experiments where the 2-qubit gates are getting down to these kind of numbers. I mean, you have to do it in a big scalable system. But, all this can be done.
Mm-hmm. The last point I want to talk about on the architecture itself is the readout from the qubit. So can we talk briefly about that? The first question I would have is why it's connected to the qubit itself in this kind of architecture, given that we have a quantum memory as well. I would expect this to be the case, that you have a readout directly connected to the qubit in, let's say, newer systems that are being built if you don't have this memory component. But given the architecture that you built in this paper, where there actually are dedicated resonators for the memory, how come this readout is connected to the qubit itself?
Yeah, this is a readout that we were doing at the time. We've since gone to a more conventional readout, which was developed by the Yale group. In this particular case, the way we operated the qubit is you could put a flux in, and if you were in the one state, there would be some kind of avalanche behavior in the qubit, so the flux would change by almost a flux quantum, and that's easily measured. And that's measured with the circuit on the upper right with the two X's on the top and the small, it's called a squid, and one's able to measure the qubit switching with that. And it was a fast method, but it was a DC method, and you'd have to reset the qubit. So it worked fine at the time for the kind of qubits we were doing, but we switched soon afterwards to a more conventional microwave readout. And the thing that with this switching behavior of the qubit, you don't get that kind of nonlinear switching behavior of resonator. So that would not be a good way to measure it.
Mm-hmm. Okay, understood. But
then
maybe we can
do with the details of the time. And again, we switched the whole way we did things soon after this paper. But the key thing was using frequency tunable qubits, which we were really mastering at the time. And that we took over, and that turned out to be a really good idea.
Mm-hmm. Okay, good. But then let's scroll down a little bit to the next image that you have here. This one, I think, illustrates, well, the bus that we were talking about before and how coupling to that bus actually happens. Could you start maybe by describing the three pictures on the left-hand side here and what's being done?
Let me just, can you scroll it up just a little bit? It's been, no, could you scroll down?
Uh-huh.
I need
Okay,
to see
sorry.
the figure caption.
Okay.
It's been, the basic idea here is you put, an excitation in the qubit, and then you put it on resonance for a variable amount of time, and then measure the qubit after that time. And by varying the time, you can see the information swapping into the resonance and then swapping back out again. And that's what these oscillations are showing. And what happens is, as you put more photons into the system, using more, I think it's more qubits, then the oscillation frequency goes faster, as you expect from this. So this is just probing that swap interaction that's fundamental to using the bus. And you see it swapping back and forth, and you also see the swap frequency going up as the number of photons are in the resonance, and that's again to be expected.
Mm-hmm. Okay, so if we look at this one a bit closer, because I guess this is the key one when we're talking about how the oscillation frequency depends on the number of qubits. So we have this on the y-axis ranging from 1 to 4, presumably corresponding to the 4 different qubits that we saw in the last figure. What is the conceptual rationale for this oscillation frequency being dependent on the number of qubits that are aligned with it? To me, that's not self-evident. I don't know if it's if it is to someone with more experience in the field.
Yeah, this is a really interesting phenomenon that happens with. It's kind of a quantum mechanical phenomenon that happens with resonators. This is a property when you solve for the quantum oscillator, you see that. And I'm trying to think, kind of classically, intuitively how this works. If you think classically, and you put more, more energy in the swing, so it's swapping faster. It's swapping. As you get more energy, the energy flow has to be faster, right? In order, in order to transfer all the energy over, it has to be faster to swap there. So it kind of gives you an idea, why it's faster. But what's different classically is if you have classical system and you have a high amplitude, the frequency that the energy swaps from one mode to the other is the same. Whereas here, the frequency goes up. But if you think in the classical case, that it's the same time, but you're swapping more energy through there, something is transferring faster. And in the end, it's a basic phenomenon of quantum mechanics that, as you're swapping more, photons back and forth, then the frequency goes up. And you have to go into the quantum mechanics to understand that. But yeah, it's a kind of a smoking gun demonstration that you're really seeing quantum mechanical behavior.
Okay, and what does it actually mean conceptually? Let's say in the case where we have 4 qubits here, all aligned to the same frequency of the bus. Like in the case of 2 qubits, the example we were talking about before with transferring information from one qubit to the other kind of makes sense. Like you attune something to the frequency first, and then you attune the other qubit to sort of transfer the information. If we have multiple qubits, like more than 2, connected to the bus at the same time, what is it that we're trying to do in a constellation like that? Is there a conceptual representation for that?
And this is what's interesting about our architecture and what we did here. So you have your bus and you have your qubit. You put, it's in the one state, so it has one excitation. You bring it on resonance suddenly, and then it swaps back and forth. But what we do here is we take 2 qubits, and both the qubits are on resonance. And then those 2 qubits swap their information. And it's interesting that as you add more qubits, you can see here on the bottom right, there's 1 qubit on resonance. And the next one, there's 2 qubits on resonance, and then 3 and 4. And then when you do that, just the swap interaction goes faster. And it's kind of funny because, it's like the 1 qubit, the other 3 are affecting the swap frequency of the first one. Is kind of what it looks like. And they're all interacting together to make that happen. And it's just a basic foundation of what you expect from the quantum mechanical behavior. So the qubits are kind of interacting with each other to coherently transfer this faster.
Okay, understood. And this architecture in general with the 4 qubits was also a scaling up of a previous system, right? That you built prior to this? Was that a 2 qubit system, or like how come you had a scaling up now with 4 qubits from something prior to that? Was it just a demonstration like the one that originated?
It was a demonstration, but it was also a demonstration that we can control 4 qubits. In this experiment, you directly see that. You can control 4 qubits simultaneously and get them to interact in a way that obeys quantum mechanics. And, that's what we were trying to do at that point. People were looking at 1 or 2 qubits and getting that to work. And then we just built the 4 qubit architecture and did a basic physics to show that things work properly with 4. And, you start with that, and you start with simple physics. So, this swapping interaction to the bus and seeing the frequency change, seeing these oscillations is, a good experiment to show that you can control such a system.
Yes. Could you also describe what the density matrices here to the right indicate? Like maybe conceptually, if we start with that, why is this a good representation of what happens in a quantum system?
Yeah, this is a little bit hard to explain. Let me just say that when you have a quantum state, you have an amplitude, how much 0 and how much 1 it is, okay?
Right.
But And so on the charts to the left, things are probabilities, okay? But these quantum states also have a phase to it. Okay, so think about an oscillating signal in an inductor capacitance oscillation. There's an amplitude, but also there's a phase to the oscillation, right? So to tell what's going on there, you need to know amplitude and phase. So the probability tells you about the amplitude, but you also have to know about the phase. And the density matrix is a way to display both the amplitude and phase. So the amplitude is kind of what's going on the diagonal from left to right on these density matrices. And then the phase is kind of the off diagonal. And by looking at those signals, you can see if the quantum phase is as you would expect. And that's what these diagrams were showing at the time. And at the time we were doing these basic experiments, and we wanted to make sure that the basic quantum operation was performing properly.
Okay.
The problem with the density matrix, it works fine for a couple qubits, as we're doing here, a handful of qubits. Once you start going to beyond, let's say, 10 or so, it's just really hard to take this data, and you have to use different means. So that's what we did in subsequent experiments on lots of qubits. But for a couple qubits, a density matrix is useful.
Okay. What do you use as you scale up a system like that and you still want to get some insight into what happens? What are the other kinds of representations you could use?
Well, what you tend to do is basically do something on randomized benchmarking or cross-entropy benchmarking, where in that case you do a bunch of gates and then you measure like the probability at the end. And if you lose phase coherence and you have problems with the phase, you'll lose the coherence by doing all these complicated, you won't be able to predict the answer. So you basically look at the amplitudes at the end, see how they're dying off, and then see if they're decohering in the way that you would expect. And if it does, it means both the amplitude and phase of the evolution was good in the way that you run the gates. You don't directly measure that. And that turns out to be a little bit, it's just more scalable. You can go to more qubits. It's not quite as direct as these kind of measurements, but it's just what you have to do once you go to many qubits. You have to simplify your measurement process. You're making more assumptions, but they're good assumptions because the gates are operating properly from this anyway.
Okay. One more question on the density matrices. I think these are only for the real part of the quantum state. Like when it comes to the imaginary part of it, does that have a physical representation more than, let's say, the computational aspect of all this? Like, is there any utility in knowing what the imaginary part is as part of a readout, or is that simply something you ignore as you look at the results? The
real and imaginary parts of, let's say, an off-diagonal element is kind of a real and imaginary part of a vector on the unit circle. So from the real and imaginary part, you can directly get the angle of the phase. So the length of it tells you about the coherence of that state, and then the angle given by the real and imaginary tells you the phase.
Okay, good. For the last few minutes...
Roughly speaking, but that's a good way to think about it.
Okay, cool. For the last minutes, maybe we can talk briefly about the implementation that you tested this algorithm on as well, or this architecture on rather. So you performed Shor's algorithm with this. Would you mind just summarizing on a very high level? We won't go into the details now really of what's being done in this application, but just on a very high level, what your findings were from applying Shor's algorithm to this kind of architecture.
Yeah, first of all, when we were running Shor's algorithm, the point is to run an algorithm and see if it gives you the right answer, okay, and see if you get information out of it. Factoring 15 is not very hard, And in fact, this algorithm and many other of these algorithms are pre-compiling it. So they have a complicated thing, and then you simplify the gates so that you only have a handful of operations. In a real Shor's algorithm, you can't simplify those gates, and it doesn't work. So running a Shor algorithm on a handful of qubits is it's just a demonstration of an algorithm and not really doing that. Now, it's been quite a few years. I didn't review this, but basically you run the algorithm and you get some output states where you measure, a 0 or 1 out of your output states. And from those output states, you could then deduce what the factors are. And I've forgotten the whole way to do that. Looking at the density matrices, you see some skyscrapers that stick up, so you see some definite signal above the noise, and thus you're able to figure out, these factors. But it's clear that it works, but okay, it only works to some certain degree. But it's running a complex algorithms where, what was that? That's 1, 2, 3, 4, 5, 6, 7 gates. So that was a nice state-of-the-art demonstration at the time. Okay, now 10 years later, we're running algorithms with 1,000 gates. Okay, and getting meaningful results out of that. But at the time, that's what we are able to do with the coherence and the control of our system.
Okay, great. Maybe as a final question before we wrap up, when we're talking about these larger systems now, what is the main limitation that we're seeing for superconducting architectures when it comes to preserving the correct answer while applying an algorithm like this? So I think in your case in particular now, you got the right answer with something like 50% probability. If we're talking generally about superconducting architectures, is it the fidelity that's the key quantity, let's say, that you need to enhance going forward to make that more scalable, let's say?
And I can put in some numbers here. Let's just go to the quantum supremacy experiment. Those numbers are on my mind. We were able to make qubits with coherence times in the 20 microsecond range, okay? And then our gate operation times were about 20 nanoseconds, both in single two gates and the 2 qubit, swapping interaction. So that's a ratio of about 1,000. And that means you can do roughly 1,000 total operations before you lose memory. So if you have 50 qubits, like we did in the quantum supremacy experiment, then that's 20 operations per qubit. And that's enough operations per qubit to start doing something interesting. And one can push that a little bit more and get things to work. And of course, what you want to do is do more operations than 20 per qubit or 1,000 total. And you have to make the coherence time longer. Now, the nice story about this is people have made qubits with coherence times in the 100, 200, I think up to, let's say, around a millisecond in the best cases. So it's possible to get a factor of 10, clearly, and maybe even more, by combining the good qubits with this. In that case, you're doing 10,000 or more operations. You can really start doing some interesting algorithms. Now, you just can't say I'm going to combine the two technologies, because the way you make a qubit to have good coherence time is probably going to be different than the way that you make the qubit to have fast gates and do whatever you want. Because the reason we got it to work with this Google experiment was we made very fast gates based on this frequency tuning, and many years to understand how to do that carefully. So, you have to combine both ideas together. It's definitely possible. You can do that. People are working on it. You know, that's why I feel very optimistic about it, where, you know, you take this from, what, 2009, and then 10 years later, we were doing much better than this, and then given more time, we're going to be even better here. So we see a very good step. And yeah, this is a nice paper because it shows you that we were able to build a 4-qubit system and control it well enough to run, you know, some kind of complicated algorithm with a handful of gates. And that's a good thing. And then by improving it, going to a new geometry, we were able to improve from 7 gates to 1,000 gates.
Right.
And then we want to go to 10,000. And then by doing error correction, you can go even more. So that's the sequence we're on.
Perfect. I think that's quite an optimistic note to cut it at as well. So I think we'll end the interview here. Thanks, John, very much for taking the time.
Thank you. You're welcome. It's been a pleasure.
Great. Then let's stop the recording. There we go.